The day is here. We're starting a new chapter. We've got free energy and thermodynamics that we'll be starting today, and we'll see how it goes. We've got this quote that says, "The energy of the world is constant. The entropy of the world tends towards a maximum." That's a little bit of a precursor, appetizer for what we'll be covering today. In the universe, energy transactions you can sort of think as gambling. You may know that in gambling, if you're gambling at a casino, the house always has an edge, especially if you're on a machine. There's always a little bit of favorability towards the house, the casino. Energy transactions kind of work similarly. So our first law of thermodynamics, energy is conserved in chemical processes. This is one we've already talked about, law of conservation of energy. If you're burning gas in a car, like you do in most cars, about 20% of that energy from the combustion goes towards moving the car, and the rest of it gets dissipated as heat or lost as heat, which doesn't usually do meaningful work. Unless you're running your heater, then it's maybe meaningful work. But a lot of the energy just goes towards heat. The energy from that reaction goes towards, moving the car and towards heat, which is fine, which is normal, and not surprising. So you're always going to lose energy as heat. Pretty much almost anything that you do, you're going to lose some energy as heat. The only way that you can really, quote unquote, win in this context is like a space heater or a water boiler, where all you're trying to do is create heat. Since heat's always created, pretty much always created, that's like the most efficient application since you're just trying to make heat. The second law of thermodynamics, which we'll be talking about soon, the rechargeable battery. If a battery can do 100 kilojoules of work, it takes more than 100 kilojoules to recharge it. This isn't to say that we're destroying energy. We just can't perfectly efficiently put that energy into the battery. So this is where that heat tax idea comes from. So all of our processes, all our real world processes are less than 100% efficient. Sometimes we can get really close, but it costs a lot of money to get really close, and it's really inefficient to get a process to be really close because you have to super cool things and use really expensive technology and other things. So there's probably a lot of work that would go into getting some small process to get close to 100% efficiency. Generally speaking, generally thinking, we can't break even with our energy. We're always going to lose some energy as heat. If you're heating stuff with natural gas versus heating with electricity, when you're heating with natural gas, you have to get the natural gas into your house. So presumably there's some way that works. But once you have the natural gas, then you just burn it. It's a one-step process. It's pretty straightforward. There's some other bits and bobbles involved to make sure that you don't suffocate in your home. But for the most part, you're just burning it. If you're heating with electricity, you might be burning something way far away. There might be a coal generator, coal power plant, and that might go to make steam, which is used to generate electricity, and then you transmit the electricity over long distances, and you lose some of your electricity during that process, and there's probably some lost as heat there. And then you turn on your electric heater, and your electric heater is like 100% efficient, basically, but you lost heat everywhere else along the way where you didn't really want to lose that heat. Kind of the big takeaway is we're going to lose energy as heat. We may have, but probably didn't mention spontaneous versus non-spontaneous. So we're learning specific definitions for spontaneous and non-spontaneous. A spontaneous process occurs without ongoing outside intervention. So our spontaneous process will happen by itself. We don't need to do anything usually to get it started. It will just run on its own. Runs on its own. For a mechanical system like this person who's very dangerously lifting up this block, probably of foam, so that when they drop it on themselves, inevitably they don't get hurt. They're lifting this block of foam up, and you could see that if they let go of this rope that they're using to pull up this big block of foam, the foam is going to just fall, right? It'll fall straight down because of gravity. That would be a spontaneous process. It happens by itself. You don't need to like bat the piece of foam down to get it to start to drop. It's just going to do that on its own. So for mechanical systems, it's often easy, especially if they're simple like this. We can often tell, like, hey, that's going to happen. Hey, that car's going to roll down the hill. You better put your parking brake on. Hey, don't let that ball roll down that hill because it's just going to keep on rolling. In chemical systems, it's a little bit less straightforward. And so we need a way of predicting how the system is going to move, whether it's going to be spontaneous, happen on its own, or whether it's going to be non-spontaneous. That being said, right, spontaneous kind of just meaning that it will happen on its own does not mean that it's going to happen quickly. It just means that it will happen. It might take 100,000 years for it to happen, but it will do it by itself. You don't need to put extra energy in. So spontaneous can be slow. Just because it'll happen on its own doesn't mean it will happen quickly. There are ways that we can increase the speed, the rate of a spontaneous reaction, like with a catalyst. So a catalyst will increase the process, will increase the speed that it proceeds. If it is not spontaneous, a catalyst won't help. You would have to still put outside energy in to get the reaction to start and probably to keep going. That being said, a non-spontaneous process, one that doesn't happen by its own, is not impossible. It just needs energy input. So it will proceed, that's too many E's, proceed / react with energy input. For many of us, we have hobbies and pastimes that we like to do. Sometimes we don't get to get around to them and do them as much as we'd like. So if there's a craft or a game that you like playing, it's a spontaneous process. You'll do it. It might take you a while to remember that you like doing that thing. It might take you a while to have room in your schedule to be able to get around to doing that thing, but it's going to happen. A non-spontaneous process, like doing the dishes or doing other household chores, you're probably not going to do unless you have to. There's like some anxiety maybe building within you, or somebody tells you, hey, you have to do this because it's your responsibility as, you know, a member of the household. It's time for you to clean the dishes. That would be more of a non-spontaneous process. It's going to happen, but it needs external input. Okay, so we talked about we need some chemical potential. This was a couple slides ago here, to predict the way that a system is going to shift. So let's think about enthalpy. We've talked about enthalpy a little bit before. Could we use that as our chemical potential? So delta H, our change in enthalpy, is the same as heat at constant pressure. Our enthalpy, kind of our energy, predicts that exothermic reactions are spontaneous and that endothermic reactions are not spontaneous. Because of the change in energy. So if we're thinking about enthalpy in an exothermic reaction, we're emitting heat, we're losing heat. And an endothermic reaction would be not spontaneous because we need to put in energy. And we'll look at some simple endothermic reactions or processes that are spontaneous. To show why enthalpy cannot be used as our chemical potential, at least not by itself. For example, if we have ice just sitting out on the countertop and it's not below freezing, the ice will melt. We are not putting energy into that system directly to make that happen. It's just happening. The evaporation of liquid water to gaseous water that happens just with water that's sitting out. If you leave water out long enough, it'll all evaporate, assuming that it's not 100% humidity in the room. And sodium chloride, if you stick it into water, will dissolve. Those would all be spontaneous processes that involve an increase in enthalpy. So for the melting of ice, the water that's in that solid ice is gaining energy so that the molecules can move around past each other, not being locked in place. Evaporation of liquid water, a similar concept. Those water molecules are gaining energy and being ejected into the gas phase. And sodium chloride, something has to happen for those sodium and chloride molecules to get pulled apart. Something that those processes all have in common is the disorder or randomness increases. So entropy, rather than enthalpy, entropy, very fun idea, is the criteria, singular, for spontaneity, if something's going to happen by itself in a chemical system. The informal definition, or the informal way of thinking of it, is chaos or randomness. So like the messier the arrangement, the more entropic it is. When we're changing from liquid water to gaseous water, we're making it so that the things are no longer connected, right? The water molecules are no longer touchingly close to each other. They're spread out. They're moving all around in every which way. So it's a little bit more chaotic. It's a little more random. It's a little more spread out. In sodium chloride, the sodium and the chloride ions are nicely arranged in a lattice. And when you pull them apart, when water pulls them apart into water, they're arranged in a more chaotic, less orderly way. So that also has an increase in the chaos or an increase in the randomness of the situation in the solution. So entropy, randomness, gets the symbol S because, of course, why not? So S is our symbol for entropy. It's a thermodynamic function. So the movement of a system. It increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So more possible arrangements equals more entropy. So the more ways that you can arrange something, the higher the entropy of the system is. And we've got a definition, a math definition of entropy. So entropy is equal to this lowercase italic k, the Boltzmann constant, times the natural log of W, the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. Do you have any questions so far? All right, let's imagine an ideal gas, a fixed amount of an ideal gas. So we'll have a certain number of atoms, molecules, moles of an ideal gas. We've got constant pressure, volume, and temperature. So our state of this system, the overall general state of the system, is going to be defined by our pressure, volume, and temperature. The energy of our system is going to be constant, partly because of temperature being constant. However, if we look inside the system, if we look at the way that the molecules, the atoms are arranged, at any given moment, those will be all over the place. Every time you look at it, every frame that you look at it, if you're able to zoom in and look at the state of the gas molecules, they're going to be arranged differently every single frame of the video that you're looking at. In a particular instance, one particle might have really high kinetic energy. It might have gotten bumped by two neighboring particles at the same time. And these two particles impart a lot of energy into this other particle, so this one now suddenly has a lot of energy. And then the very next moment, this particle that had all that energy goes and bumps into another particle moving the other direction. And then you've got, I don't know why the size of the particles is decreasing, but whatever. Then you've got maybe two that are relatively low energy, or maybe this right one has a ton of energy. Who knows how it works? Just the idea being things are going to change. There's a lot of energy transactions happening, even though the overall energy is the same. So this brings us to an idea of a microstate. So what's going on inside at one instance. So for our overall system, energy is constant. We've got the same pressure, we've got the same volume, we've got the same temperature. We also have the same number of molecules or atoms going on in the system. But small scale, some particles have lots of energy. Others have little energy, not as much energy. And that's constantly changing. So that microstate changes constantly. All of those little energy transactions, the particles bumping around, some of them moving fast, some of them moving slow. On average, the same energy the entire way through. That's our macrostate. The microstate, lots of possible little arrangements for our energy. So the W that we saw in our S equals K ln W. That W, the number of arrangements that we have, we can think of as the number of possible microstates. Obviously, if we get up to a large number of particles, we can't, us personally, we can't calculate that. But we can think about some simple versions, some simple systems where we can calculate it. So the number of possible arrangements of our energy, the ways that we can distribute our energy between our particles within a given macro state, within a given total pool of energy, how can we distribute all the money, all the energy? So let's look at two systems. So we've got system A and we've got system B. These are two systems with two particles and a total energy of 4 joules. Each of the particles has to have, we're thinking only in integer values of joules. So system A has one energy level, just has 2 joules, and so it only has one possible microstate. If particle blue has 2 joules, particle red has to also have 2 joules since our total energy is 4 joules. System B, we've got 3 joules and 1 joule as our options, but we can switch those values. So we can switch the colors to get this second microstate. And because there's 2 possible options within system B has more entropy. Because of more possible arrangements. So more possible arrangements is more entropy. The difference between system A and B, we could think of those maybe as being like, we've got electrons in orbits around a nucleus, and one of these, our only option that we can access is that 2 joule energy level. And then the other one, because of the way that our energy levels are distributed, we can access 2 different energy levels. That might explain how we would get this difference in systems, rather than just having random amounts of energy. Okay, so entropy increases with the number of energetically equivalent ways to arrange the components. This whole bit, this is basically just our definition for that W term. Another takeaway, the state with the highest entropy also has the greatest dispersal of energy. We can spread out our energy more. We can move our energy around more. More ways or options to distribute the energy. And then our last bullet point here, a state, like a macro state maybe, in which a given amount of energy, whatever amount of energy that is more highly dispersed. If we've got really spread out energy, that's going to have more entropy than a state where we've got a lot of our energy concentrated in one area or in a couple of particles. Because the energy is spread out more, we've got more possible states with the amount of energy that we've got, versus if all of our energy is concentrated into one area, fewer particles have the energy, there's fewer states that we can make without spreading that energy around to the other particles. So our second law of thermodynamics, our first law was that energy is constant. Our second law is that for any spontaneous process, something that happens on its own, the entropy of the universe increases. So the change in entropy, the delta S of the universe, is greater than 0. We're adding entropy. Entropy increases, energy dispersal increases. For the universe. So we might be able to, the reason that it specifies for the universe, we might be able to decrease the entropy of there might be a process that decreases the entropy of that process, but increases the entropy of the universe, and so it's still spontaneous. Entropy is also a state function. So our change in entropy depends on initial and final states, final values. The journey or path is not important. We don't need to know anything about how we got there. We just need to know where we started and where we ended. Which is just, again, our definition for a state function. It's been a couple months since we talked about those. So our second law of thermo, a chemical system proceeds in a direction that increases the entropy of the universe. Let's think about this container. In the left side of this interesting little container that we've got, we have 4 particles. On the right side of the container, we've got no particles, so we've got a perfect vacuum, and we've got a little stopcock keeping those 4 particles on the left side of the container. Since this is an ideal gas and it's expanding into a vacuum, it's increasing its volume with no change in pressure. It's not acting against external pressure. If you remember a few chapters ago, that would be work if there was an external pressure. So the work that's done is 0. So we're not changing our total energy because we're not doing work. No work done, no energy. But by moving these particles, some of them over to this other side, we're increasing the entropy. We're spreading out our energy. So thinking of a system that's got no change in enthalpy, doesn't do any work, but is increasing in entropy, randomness, chaos, energy dispersal. So when we open that stopcock, there's a couple of ways that we could arrange those particles. Here are 3 of them. So here are 3 macro states. So we've got state A and state B. We've got 4 particles on the left side or 4 particles on the right side. Those are both entirely possible. It could be that they don't actually expand, or they go over to the right and they come back. And for state B, maybe they all migrate over to the right side and none of them come back. And then for state C, 2 of the particles stay, 2 of the particles go. So these are 3 different macro states, 3 different arrangements of our particles. How many possible options do we have? How many arrangements do we have for putting particles into each of these states? Let's look at that. So our atoms are identical, but we can label them 1 to 4 since they are actually different particles. For states A and B, we have 1 microstate. So our macrostate, 4 particles on the left. Our microstate is also 4 particles on the left. We're not thinking about like how they're arranged relative to each other, just are they on the left or are they on the right? And in this case, they're all on the left, and in state B, they're all on the right. And you could shuffle them around until they look exactly the same as what we've got in the picture. So for these, we've got 1 microstate. For our state C, we have 6 different microstates. So we had 2 particles on the left, 2 particles on the right for our overall set of circumstances. And we can have particles 1 and 2 on the left and 3 and 4 on the right. But we could also swap some of those. So we could have 2 and 3 on the left, 1 and 4 on the right, 1 and 3 on the left, 2 and 4 on the right, and so on. So we have 6 different unique arrangements of the particles. Again, just thinking of this as in terms of left and right side. Which particles do we have on the left side? Which particles do we have on the right side? Not thinking about their location within those left or right sides. And since we've got 6 different unique arrangements, we're much more likely to find our atoms in state C versus in state A or B. State A and B are both possible, but we've got fewer options, fewer microstates for those. And so it's more likely that we're going to find it with 2 particles per side because there's many more arrangements where we can find them all on one side or the other.
So do microstates kind of just focus on the arrangement?
For this example, yes. We are just thinking of, are they on the left or are they on the right? There's lots of other ways that we could think about it. So like there was an example earlier where microstates was energy levels. So we had a system where we had 2 joules as our only energy level, and we've got 4 total joules of energy in 2 particles. Since we only have the 2 joule energy level, each of our particles has 2 joules. There was another one where we had 1 joule and 3 joules as our options. And so we could have 1 particle on the 3 joule and 1 particle on the 1 joule, but we could also flip them. So particle, they were colored in that one. So we could have 1 in the higher energy and 1 in the lower energy, but we could flip which particle has the energy. And so then we would have 2 microstates. So that was like an energy version. Here we're looking at left-right. If we increase the number of atoms up to 20, then we get 184,756 microstates for state C. And again, the microstates for states A and B, where all of our particles are just on one side, remains 1. We only have 1 arrangement where all the particles are on the left side and 1 arrangement where all the particles are on the right side. So our many, many microstates of equal numbers of atoms on both sides, that's where we get the most combinations, the most possible arrangements. Or at least we get many more arrangements than if they're all on one side or the other. So we would expect that equal number of atoms on each side to be the dominant state. the change in entropy from state A or B to state C is going to be positive. So we've got many states for equally dispersed atoms. So we've got a really big W. And for A and B, one state. That's the smallest W that we can get. And since S is this Boltzmann constant times the natural log of W, the bigger W is, the bigger S is going to be. So moving from the state with one option, W is going to be very small. So entropy is going to be very small. So our initial state, very low entropy. Our final state, because W is now enormous, our final state has much higher entropy, and so our change in entropy is positive. So since we have a positive change in entropy, the system or the process is spontaneous or non-spontaneous. It is spontaneous. So all that needs to happen is you open that stopcock, you let the particles move from one side and disperse themselves, and they will do it. You don't have to give them any energy. That gas is going to spread itself through that glass. So thinking of it in terms of energy dispersal, when the atoms are confined, when they're only on the left side or on the right side, we've got all of their energy contained into that small area. But when we evenly distribute our atoms across both of the flasks, then we get our energy dispersed. Our energy is spread out, which correlates with higher entropy. A decent amount of the entropy stuff we can just, we don't necessarily have to think of it in like physics type thermodynamics stuff. Like you probably could have predicted without us having to talk about microstates and macrostates, you probably could have predicted that if we open this stopcock, the gases are going to be evenly distributed, rather than all of the molecules or all of the atoms being on one side versus the other side. You probably could have predicted, yeah, they're going to be evenly spread out. The second law also explains things that aren't explained by the first law of thermodynamics. The energy is conserved. For example, in ice water, heat travels from the water to the ice. The ice absorbs heat from the water. Our first law doesn't prohibit our ice becoming colder. So like our ice could get colder and our water could get hotter. Our water could take energy from the ice and the ice gets colder and the water gets hotter. We know in practical experience that's not the case, right? The temperatures of the ice and the water move towards each other until all of our ice is melted and our water is all the same temperature. And that follows with the second law. So our experiences line up with what we see for the second law, that our energy gets dispersed rather than it all being concentrated into a little bit of hot water. So energy spreads out. Part of our second law. So hot water, or warmer water at least, gives energy to the ice. The ice absorbs the energy. The entropy, the number of arrangements, the dispersal of the energy, increases from solid to liquid and liquid to gas and solid to gas. If we're thinking of randomness, we're thinking of chaos, our gas state is more disorderly than our liquid state, and it's also more disorderly than our solid state. In our gas state, our particles can be all over the place. They can exchange energy with each other. We can have really high energy particles, really low energy particles, and then the next moment that can change. And in a liquid, they're all kind of clumped together, condensed together. I feel like talking about it in terms of like how many possible states you can have starts to get confusing when you're thinking of a gas, because like how do we define where a position is for the gas? It's a little confusing to me, but we can think of just they can not be touching their neighbor, and so there's more ways that we can arrange them because of that. It also works nicely with dispersal of energy since they are more spread out. We've also got more ways to distribute, more ways to use the energy. Versus in a solid. So thinking about our lowest entropy state of a solid, our highest entropy state of a gas. In a solid, especially for something like water, where it's ideally we're going to line up our polarity of our water molecules, they're all going to be locked in place. They're not going to be rotating. They're just going to be vibrating around in their spot. And the bonds are also going to be jiggling. So in a solid, we're limited to little vibrations moving side to side, up and down, maybe a little bit of waggling on some of the bonds. If we are in a gas, then our gas can be moving around rather than just vibrating, and they can also be spinning. So our gases can use energy in more ways. Has more uses for energy. Less confined. It's got that freedom to move around. Rather than just wiggling its bonds or bumping up against its neighbors. It can go for a walk. It can do a little dance. All those sorts of fun things. So that is also higher entropy. These are all of the phase changes that we'll really talk about. So for each of these possible options, our entropy is increasing, our delta S is greater than 0. If we're moving from a solid to a liquid, in a solid, our particles are just vibrating in place. In a liquid, they can swap places with their neighbor in addition to doing those vibration movements. So they've got more ways to use their energy. The phase transition from a solid to a gas, our solid state again, right? They're just vibrating in place. And in our gas, as we saw, they can be rotating, they can be moving in straight lines. They've got more ways of using their energy. So more ways to use the energy to express the energy. So they have more entropy. Our phase transition from a liquid to a gas. In a liquid, all the atoms, the molecules, the particles are all clumped together. In a gas, they're all dispersed. We've increased the dispersion. And dispersal of energy is one of the things that drives entropy. So a couple of things that we could think about for our phase changes. Another thing that will increase entropy is increasing the number of moles of a gas during a chemical reaction. So more particles means more possible states. So in that example with particles on the left, particles on the right, stand up, sit down, fight, 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 and particles in the middle. When we had 4 particles, we had 6 options for evenly distributing our particles. When we jumped up to 20 particles, it was the 180,000 or something. If you increase the number of particles, you can increase how many particles do you have on the left, how many particles do you have on the right. You can increase the number of particles on each of the energy levels. All right, predict the sign of delta S for each process. Are we increasing entropy? Are we decreasing entropy? So we've got water boiling, iodine switching from a gas to a solid, calcium carbonate turning into calcium oxide and CO2. That was a small amount of time to think. So what do we think? For water boiling, thinking about water evaporating in the process of boiling, is the change in entropy. Is the change in entropy positive or negative? Positive. Why is it positive? Going from a liquid to a gas. So we're increasing the ways that our water molecules can move around. We've got rotating, we've got moving in straight lines. We're also dispersing our energy. We're spreading it out across a larger volume. We've got more places that our molecules can be. They're not all just touching each other contained to our container that we're boiling the water in. So dispersed energy and also more ways to express the energy, the rotation, the translation, etc. How about iodine going from a gas to a solid? What is our change in entropy? It is negative. Why is it negative? We're going from a gas to a solid. We are concentrating the energy. We're condensing, pushing all of our energy down into a smaller area. And we also, because of that and because of the iodine molecules getting locked into place as a solid, we've got fewer states possible, fewer ways to express the energy. The iodine molecules are no longer able to rotate, they're just vibrating in place. So there's less freedom, there's less chaos. How about our last one, calcium carbonate, turning to calcium oxide and CO2? Positive. Why is it positive?
Because he formed a gas. So entropy goes up.
We did form a gas. So the gas is definitely going to be a higher entropy state. Is there anything else?
Is it because there's two things?
Yeah, there's two things. Just two things, and that's all I need. So the number of particles increased. And since we have more particles, we've got more ways to spread our energy out. We've got more possible ways of distributing our energy to every one of our particles. We could count them all out if we had the time, and we don't. So our number of particles increased, and so we've got more possible states. More possible microstates. With different energy levels or with putting things on one side or the other, being our two examples. A change in state, solid, liquid, gas, is accompanied by an exchange of heat, Q, between our system, the thing that's changing the state, and the surroundings. So like if we think about water boiling or water melting, water is the system. And there's an exchange of heat between the system, the water, and its surroundings. Water in a pot on the stove, a gas burner. The burner would be part of our surroundings. Just to try to place some like concrete things into our mind's eye for this. So entropy, as we've talked about quite a bit, is related to the distribution of energy. More dispersed is more entropy. More possible states is more entropy. For the change in entropy, when a system exchanges heat with its surroundings at a constant temperature, so our water, if it's boiling, is going to be locked in at a specific temperature. That's something that we hopefully remember from 3A or 1A. We're exchanging some heat. It's a reversible process because we can take the liquid to a gas, we can move the gas back into a liquid. And our water at least will be at a constant temperature. And we can calculate the change in entropy associated with that process. So in the water boiling example, our Q reversible, we're adding water into our system. We're adding heat into our water, which is our system. Adding heat to water. Also changing from liquid to a gas, delta S is increasing. We're increasing our entropy. We know that we're increasing our entropy because we're moving from a liquid to a gas. Gas has more entropy than the liquid state. We're also adding in heat. So this works out with our equation. Q reversible is increasing positive heat to the water, and then our temperature is just some constant thing. And as it often is, our temperature has to be in units of kelvins. So entropy is a measure of energy dispersal per unit temperature. How spread out is our energy? How's our energy distributed at a specific given temperature? So joules per Kelvin makes sense within that definition. When we have a substance that melts, it absorbs energy from its surroundings. So this delta S equals Q rev over T. So if you plop an ice cube down on the countertop and it's not freezing cold inside, the Q of that system, the Q of the ice, it's absorbing energy from its surroundings. Absorbs energy from its surroundings. It gets dispersed into the system. When the system melts, its entropy is increasing because it's moving from a solid to a liquid state. So the entropy of the system increases. The temperature of the room, of the system, overall temperature should be roughly constant. All right, what are reversible processes? A reversible process is a process that can be reversed. Hey, isn't that dandy? We're defining it in the slides, though, as something that reverses direction upon a very small change in a property, the smallest little change in a property. For example, ice melting in surroundings at right about 0 degrees Celsius. If the ice is melting and it's at its freezing point or it's at its melting point, if it's melting, if we make some small change in the heat, it no longer has the energy to do the melting because we're right at that melting point. Melting is a gain of energy for, in this case, it's water as ice. If we take away a little bit of that heat, then our molecules no longer have the energy to move past each other and they're going to get stuck. This works when we're at 0 degrees Celsius. It'll stop melting and it'll refreeze. So that makes it reversible. It's a small change in energy. If we have ice melting on a countertop at room temperature, that is irreversible. It's going to move in one direction, and just taking a little bit of heat away from it is not going to cause it to go back the other direction. So reversible processes change direction with tiny changes in heat and other properties. Like we might change pressure or volume or some other thing like that and cause a reversible change. Calculate the change in entropy that occurs in the system when 10 grams of acetone vaporizes from a liquid to a gas at its normal boiling point. We'll need our delta S equals Q rev over T. So we're being asked to calculate the change in entropy. That's the delta S from our equation. We are given a temperature. So that means that we need to find Q rev. Q is heat. Often having units of joules. So we need to find something in joules. We are given an HVAP, a change in enthalpy, that conveniently has joules in it. So if we multiply our change in enthalpy by something that's in moles, that'll give us heat, which is what we want, so we need moles of something. So 29.1 kilojoules over moles. This would give us kilojoules. So we need moles of something. That something is going to be our acetone. So that's roughly what my brain is doing to solve our problem there. To get to moles, we're starting with 10 grams of acetone, C3H6O. To get to moles, we'll need to divide by our molar mass. Our molar mass for acetone, 58.08 grams per mole. So we have 0.1721 ... moles C3H6O. Multiply that by our 29.1 kilojoules per mole. The moles cancel. I guess that would be moles C3H6O. It's the ugliest H I've drawn in a while. .01013 ... kilojoules, or 5010.3 ... joules. .3 joules over our temperature. What value are we putting in for temperature? Kelvin, exactly. So 56.1 plus 273, optionally add the 0.15. 329.25 Kelvin. And we get a final value for our entropy, change in entropy rather, 15.2 joules per Kelvin, which feels like a nonsense unit, but is not. So the level of energy dispersal that we've gained is 15.2 joules per Kelvin. Questions about the math part of that problem? Entropy is fun because it sort of feels like it doesn't make any sense. At least that's how I feel. Like it does make sense, but it's really hard to make it relate to real things. Water freezes at temperatures below 0 degrees Celsius. How does the entropy of the water change? Is the process spontaneous? According to our second law of thermodynamics, for any spontaneous process, the entropy of blank increases. Think about what should go in the blank. Yes, the universe goes in the blank. The entropy of the universe increases. The entropy of the water when it's freezing or change in entropy is negative. Because we're going from a liquid to a solid. So it might seem at the surface level like this process is not going to be spontaneous from a purely thermodynamics perspective, right? We know, possibly not in our own personal experience because it like never gets freezing cold here, but we know if you leave water out overnight for some reason, or if there's condensation on the hood of your car and it gets freezing cold overnight, you walk outside, the ice will be frozen. So we know that it is spontaneous. It happens by itself. In a thermodynamics perspective, it's spontaneous because the entropy of the universe is increasing. So even though the entropy of the water decreased, we decreased the entropy of the water, the entropy of the universe increased because of the energy that was taken out of that water. So we can distinguish between our system and our surroundings. So in our example of water freezing, water is the system. Generally speaking, the system is what we care about. Our subject. The thing that's in focus in a picture. And the surroundings is everything that's around it, everything that's not the system. So the air that's around the water, the surface, the thing that the water is sitting on, like the hood of your car. It could be inside of a glass. It's the flowers in the planter bed across the street. It's the airplane that's flying up in the sky and leaving chemtrails. The entropy of the system can decrease as long as the entropy of the surroundings is increasing by a greater amount. So for delta S universe, for the entropy of the universe to be positive, for the entropy of the universe to be increasing, the change in entropy of the surroundings needs to be greater than the change in entropy of the system. Does that make sense? That might not be written correctly. That statement might not be correct mathematically, but hopefully the idea is coming across anyway. So for example, if the change in S for the system is negative 58 joules per Kelvin, then delta S surroundings must be greater than, yeah, there should be a negative there, must be greater than 58 joules per Kelvin. So I added a negative in there, and I think that fixes it. And then since this is the 3 of 3 for how heat transfer and entropy changes, the reason that freezing water increases the entropy of the surroundings is freezing is exothermic. The water is losing heat. That energy is going into the surroundings. It's dispersing. Entropy is the dispersal of energy. Since we're dispersing our energy, we are increasing our entropy. And this is a graphic of what these might look like. So I'm going to make a bar. So that bar, that blue bar, is the size of the delta S system. So if we stack up the size of our delta S of the system, right, the difference, that's our change in entropy of the universe. So we can see slightly positive. Questions about entropy? Cool, we'll pick up here next class.